Hello again. So now that we have the idea of a function of more than one variable, we can now start doing some calculus with those functions. And for the time being, we'll start with just a function of two variables, say x and y. Right? And now we're going to define what a limit is for such a function. Right? So you have a function f. It's a function of x and y defined on some open domain D. And we're going to let L be a real number. Right? L, of course, will stand for the limit. Right? And so this is the notation we write, right, when we're taking a limit of a function as the points x and y approach a specific point x0, y0. Right? So that limit will be equal L, right? If L is a real number, then that limit exists. So here's the definition, right? For any given number epsilon, there exists another number delta, such that in absolute value, the difference between the value of the function and L is less than epsilon, right? So what that means is L and the z values, right? Remember, z is the values of the function, are very close together, right? They're within epsilon of each other. So that has to happen whenever the square root of x minus x0 squared plus y minus y0 squared is less than delta, right? So, yeah, so let's unpack all this, because I know that's a very confusing statement, especially if you haven't really seen these epsilons and deltas before. When I teach Calc 1, I go through the definition, but we really don't get into the details of it. And we don't do like really specific examples where we use the epsilon delta definition. But here it's a little more essential to the idea here, right? So here's the way to think of it, right? We have the xy plane, close enough. And we have the domain. Let's suppose this is the domain of the function, right? And so what the function does is it takes a point, let's say right here, and let's suppose that that point is specifically x0, y0, right? And it takes that point and it maps it to, well, the z-axis, right? Or if it helps, think of the z-axis as the vertical axis. That's fine, right? So, yeah, so let's say f of x0, y0 is equal to this z here. We'll call it z0, right? Or z0. Okay. So, if I draw around this original point here a small disk of radius, let's say delta. I know that's very small here, but so this radius here is delta, right? So you can see why you get the square root of, this x minus x0 squared plus y minus y0 squared. That should remind you of essentially a circle, right? So if x and y represent any point within that circle there, so let's suppose this little red dot here, that red point has coordinates x and y, right? As long as that point is within delta, what that does is that guarantees, right, that if I take the value of that function, and maybe I should use a different symbol here, right? So this will be z, which will be f of xy, right? So that will guarantee that z will be within epsilon of the z0 here. So this could be, z0 plus epsilon or z0 minus epsilon. So somewhere in this band has to be the value of the function, has to be z, right? So that's the idea. I know I'm erasing everything here. So yeah, so this is z0 plus epsilon. This is z0 minus epsilon. And so anywhere in between, your z could lie, right? So if the z happens to be outside of that interval, then we don't get a limit, right? So that's the idea. So essentially, right, the closer that this x and y is to x0, y0, that's the point right here, then the closer z will be to z0, right? So that's what we mean when we say that the points x and y approach x0, y0. They get closer to it. So, right, so I can have my xy over here. Now that's pretty far away. Right, that's pretty far away. So that's not within delta, which means for that z here, that might be outside the interval from z0 minus epsilon to z0 plus epsilon, right? However, if those points get closer and closer and closer to x0, y0, then the z values get closer and closer to z0. Okay. So yeah, this is a little bit trickier than it was in Calc 1, right, where you had this interval instead of a disk here, right? So that's the somewhat trickier thing about this is that these x, y points can approach x0, y0, right, from the left or from the right, as that would happen in Calc 1. But now you also have from above or from below or from this angle or from this angle, or it doesn't even have to be a straight line. You can approach like this, right, on a curvy line, right? So yeah, there's no left and right-handed limits like there was in Calc 1, right? Because you can approach from any direction. Right? So that's what makes this a little trickier here, right? On the other hand, right, from your ordinary Calc 1 rules, we can extend that to, calculating limits for very simple functions. So let's say, right, x and y are approaching the point 2, -3. So x is approaching 2, y is approaching -3. And we just have the function, let's say x squared plus y squared. Right? So how can we calculate that? Well, right, the difficult way is to use the definition. And I don't think we really want to use this here, right? But we will go through the idea here again, right? So here's your domain, and your function maps it to, again, the z-axis here. So this is the xy plane, the z-axis. Yeah, so x is 2, right? Y is -1, 2, 3. Go down a little further here. Right, so we're approaching the point 2, -3, right here. Right. So what is, right, the function f is x squared plus y squared. Right? So what z value is that approaching, if anything? Right? Remember, the limit may or may not even exist. Right? If f of x does not get close to any L here. Oh, L, of course, is z0. Yeah, sorry, that's the limit, is the z0 here. Right. So what's the L here? What is this approaching? Right. So if I take any set of points, and they're getting closer and closer, right, to this given point, 2, -3, right? What are the z values getting close to? Right, say right here. Well, right, so officially, right, you have to figure out your epsilon, right, your tolerance for how far away your z's can be from L. Okay, so if this has a limit, right, the z values here cannot be much further from L. They can be as big as L plus epsilon, L plus epsilon, or as far below it as L minus epsilon. Okay, so the question is, how close, right, do the x and y's, does the point xy have to be to 2, -3? Right. On the other hand, you know from Calc 1 that really nothing goes wrong here, right? If x is approaching 2, then x squared is approaching, well, 2 squared. And if y is approaching -3, then y squared is approaching, well, 9. So you just get 4 plus 9, which is 13. So my L has to be 13. Okay. Right, now I cheated here, right? Right, you don't calculate a limit by plugging in these numbers, the 2 and the -3. But that's exactly what I did. So that's cheating, right? You're not really allowed to do that. So here's what I'm assuming, right? I assumed under the assumption, right, that x squared plus y squared is continuous. Right? You know that x squared is continuous. You know that y squared is continuous. When you add two continuous functions, you expect to get a continuous function. Okay? So here's the definition. Right? We say that a function f of x and y is continuous at a point. I want to use a and b, but that looks like an interval. So we'll stick with x0, y0. Right? If, when we take the limit as x and y approaches x0 and y0 of the function f, right? If that limit happens to equal f of x0, y0, then we say it's continuous. Right? So this doesn't always happen, of course. But when it does, it's a nice function. It's a continuous function. So, right, so knowing that x squared plus y squared is continuous allows us to find the limit by plugging in the 2 for x and -3 for y. And then find the limit on the assumption that we have a continuous function. Okay. Unfortunately, though, if the function is not continuous, then you cannot find the limit this way. In fact, in that case, it may not even have a limit, right? The function might not have a limit. So, yeah, so going back to this definition here, right, this L, of course, does not have to be f of x0, y0. In fact, maybe this is a little too misleading here, that this was f of x0, y0. We assumed here that this is continuous, and it doesn't have to be. It doesn't have to be, right? So L could be something other than, right? The limit does not have to be f of x0, y0, in particular if f is not continuous. Okay. Right. So, yeah, if you don't understand the epsilon delta definition, then hopefully you understand limits from Calc 1, and you understand what continuity is from Calc 1. And it's very similar, except for the fact that we're dealing with disks and not intervals. And so that does make calculating limits a little bit trickier. Okay, so for our next example, we will do one of those tricky ones. We want to evaluate the following limits. So the points x and y, xy, are approaching the origin, right, 0, 0. And our function, f of xy, is right, so this rational function, x times y divided by x squared plus y squared. So what could that limit be? Well, if this function is continuous, we can find the limit by plugging in x equals 0 and y equals 0. Can we do that? 0 times 0 for the numerator, and then 0 plus 0 for the denominator. We get 0 divided by 0. And you know from Calc 1 that this is not an answer, right? So this is wrong. 0 divided by 0 is indeterminate, right? It's meaningless. It's not a number. So that's not our L. That's not our limit, right? So yeah, this being indeterminate, see, right, means that this is not an answer, right? So this is not equal to L. That cannot be our limit. Right. So what does that mean? Well, it could mean that there is no limit, but that's not necessarily true either, right? You've seen functions from Calc 1 where 0 divided by 0 is indeterminate, and yet it does have a limit. The limit could be, 2, or -7, or 1/2, right? Or pi squared. It could be any real number. So 0 over 0 does not mean that there's no limit. It just means that there doesn't have to be a limit, but there could be. So, right, so now what do we do? Well, in Calc 1, you would say you take your function and maybe you simplify it, right? See if you can factor something. Can you cancel something? Yeah, unfortunately in this case, no. This is about as simple as it gets, right? So let's study this function a little bit more carefully. This is x times y over x squared plus y squared. Okay, right? So here's the issue. We're looking for points that are getting close to the origin. So here's our little disk of radius. Radius is delta, right? And we want our points to get closer and closer to the origin here. And when that happens, what can we say happens to z? Do they get close to anything? Okay. So again, the tricky thing is that, right, you can approach not just from this direction, you can approach from this direction, right? Or your points might do something like this and kind of spiral inward, right? So in general, this is a very complicated way to calculate a limit by taking all the possible directions, right? But we're just gonna go in a straight line, and most of the time that's not going to get you into trouble. So what constitutes a direction if you're approaching this way? Well, how about the angle, right? All these points on this line here have the same angle with respect to the x-axis. Right, so this to me suggests using, r and theta, using polar coordinates. Right? Again, you don't have to do this, but this is one possible way to figure this out. Right, so let's switch to polar coordinates. Right, remember x. Hopefully you remember x is r cosine theta, y is r sine theta. Right. There's no cylindrical coordinates because there's no z here, right? It's a function of only two variables, x and y. Right, z is the value here. So let's just plug these in here, right? X is r times cosine theta, y is r times sine theta. And in the denominator, well, you can work this out, but you just get r squared, right? X squared plus y squared is r squared. So this is really r squared times sine theta times cosine theta, all divided by r squared. Right, so that's convenient because, right, r squared divided by r squared is 1, and they cancel. So we've rewritten this in terms of just theta. This is sine theta times cosine theta. Right? So you can think of the function now, r now, as a function of r and theta. And it turns out to be totally independent of r. It doesn't matter what r is, but it does matter what theta is. Right? You could, of course, also write this as 1/2 sine of 2 theta. But either way, it depends on theta. Right? And so, right, so different directions, let's say theta is 0, you're just going to get 0. But if theta is, let's say pi over 4, right, which is your 45-degree angle, right, you get a different value for all these functions, for all these points here, right? You get square root of 2 over 2 squared. I think you just get 1/2. So already you get two different values for two different approaches, two different angles here, right? Theta equals 0 is approaching along the x-axis, sorry, messed that up here. Theta equals pi over 4 is that 45 degrees. And of course you get two different values. So if it depends on which direction you're going in, then there simply is no limit, right? It has to be the same no matter what direction you go in. As long as you're getting close to the origin, whether it's this direction or this direction or this direction, right? All possible values of theta, all possible angles, have to give you the same limit. So that doesn't happen here, right? So to answer the question, what's the limit? The limit does not exist. Okay, and again, we didn't know that. Just because you get 0 over 0 doesn't mean the limit doesn't exist. Okay, so let's do another one. So here's another one. We want the limit as x and y approach 0 and 0 of the function y squared over the square root of x squared plus y squared. So you can see not completely, different from the previous function, but a little bit different, right? Yeah, so again, you can try plugging in 0 and 0. If you do that, you just get 0, 0 squared is 0, divided by the square root of 0, which is 0. You get 0 over 0 again, which is indeterminate, right? So that doesn't work, right? 0 over 0, indeterminate, right? So that's not an answer. Right. However, the technique we used earlier, switching the polar coordinates, that would work here. If you want another way to do it, you can think of doing it this way. If you're approaching along a line, right, what distinguishes, right, these lines? Well, they're angles, of course, or you can use the slope of the line, right? There's a slight disadvantage to that because if you're approaching on the y-axis, remember vertical lines don't have a slope, so you would have to treat that case separately. So you can also just make the substitution y equals m times x, right? Well, the problem is, right, you're approaching the origin here. You're approaching 0, 0. So if you're approaching a different point, then the lines get a little more complicated because then you're going to have a different y-intercept, right? But if you're approaching 0, 0, the origin, then y equals mx will work just fine here too. So maybe let's try it that way. Right? So yeah, again, we're approaching anywhere along this line. So notice that's actually two different angles. That's this angle, and then that's this angle, which is theta plus pi going halfway around. So, if you get two different answers from the two different thetas, then, this does not distinguish between these two different angles here, because it's the same line with the same slope. So that's another thing you want to be careful of. So I generally would switch to polar coordinates, but I don't think we're going to get into trouble here, right? So our function f of x, y is y squared over the square root of x squared plus y squared. And now we're just going to make the following substitution. Instead of y, we'll use m times x. Right, so you're going to get m squared times x squared in the numerator. You're going to get the square root of x squared plus m squared times x squared in the denominator. And so what happens here is you can factor out the x squared. So you just get x. Technically, it's the absolute value of x, but I don't think that's going to matter in this case here. In particular, one of the x's will cancel. Right, so you just get m squared times x over the square root of 1 plus m squared. And so, right, any point along this line here will have the same value. Oh, I'm sorry, except for x. X could be different along these points, right? The x's will be different. Okay, so yeah, what happens as x approaches 0? Right, so all these x's here. Right, so effectively, we can calculate this by just taking the limit as x approaches 0 of m squared over the square root of 1 plus m squared, all times x. Sorry. Well, right, presumably m is a constant, right? M is a number. And so whatever number this is times 0 gives you 0. So this limit should be 0, right? The only thing you have to worry about now is, right, that you don't get 0 divided by 0. So you better make sure that when you do this, the denominator is also not 0, right? But you can quickly see that, right? If m is 0, then this is going to be 1. And if m is anything other than 0, it's going to be bigger than 1. So it's greater than or equal to 1, which will never be 0, right? So yeah, the denominator will never be 0. So, yep, in this case, the limit is 0. Right? And you would get the same thing if you switched to polar coordinates using r and theta like we did up here. In fact, this is the way I would do it, using r and theta rather than using the slope. But in most cases, you get the same answer. And when you don't, it might be because, remember, if you get one answer approaching on the y-axis, right, where x is 0, right, essentially x is 0 for all of them. What's different is the y. And so this won't work because a vertical line does not have a slope. So you'd have to treat that case separately. Right. And we can do that here. We can just, relabel this as x equals, k times y, and just use k instead of m. Right? K is just the reciprocal of the slope, right? Which in this case I think would be 0, and so your limit would still be 0. But yeah, so in this case the limit is 0. In this case the limit did not exist. So once again, when you get 0 over 0 by plugging in the numbers, plugging in 0 and 0 here, right, that does not mean the limit does not exist. It does not mean the limit is 0. It could be anything. It's indeterminate. Okay. So 3, I think, really good examples here. Oh, and I should say, of course, that the first example, right, the function was continuous, right? Right. So the function x squared plus y squared is continuous. In fact, it's continuous everywhere, not just at the origin. The second function here, this function here, or this one down here, right? This is not continuous at the origin. So f is not continuous at 0, 0. It is, however, continuous everywhere else, just not the origin. And, well, that was the sticky point, right? That was where we're approaching 0, 0. But if it's not continuous at 0, 0, you cannot plug in 0 and 0. Likewise, this last example here also, right, not continuous at the origin, at 0, 0. It is continuous everywhere else, just not at the origin. And you can see why, because that's where you're dividing by 0. That's right. It's only when x and y are both equal to 0 that the denominator is also 0. Everywhere else, the denominator is positive. Right. And the same thing was true in example 2. Okay, so our first theorem of the chapter, I think, Theorem 13.1. Suppose k is a real number and f and g are two continuous functions, right? So they could be continuous at a point, x0, y0, or they can be continuous, say, on an entire domain, or let's say on a disk or something, right? Then the following are also continuous at that point or on a disk. K times f, right? So any number times a function will still be continuous. F plus g, right? When you add two continuous functions, you get another continuous function. And that also means if you take f minus g, right? If you subtract two continuous functions, you get a continuous function, right? The idea there is, right, your k could be -1. So -1 times g is continuous, and f plus -1 times g is continuous, but that's the same as f minus g. So if f plus g is continuous, so is f minus g. F times g, right? The product of two continuous functions is also a continuous function. And f divided by g, the quotient of two continuous functions, is also a continuous function, provided that the denominator, of course, is not 0, right? Because if you divide by 0, then that's not good, right? Then it won't be continuous then. So as long as the denominator is not 0, right, the quotient of two continuous functions is continuous. And so we use these all the time, probably without even realizing it, right? So here's an example. Okay, so our function, again, function of two variables, x and y, is just 2x minus y over x plus y. Okay, so this is a quotient of two functions, and you should recognize 2x minus y is continuous. After all, it's k times a function x, right? And then the difference of two functions is continuous. So sure, 2x minus y is continuous. And the denominator, x plus y, is also continuous. Okay. But remember, because it's a quotient, right, that denominator better not be 0. So let's plug in the actual point, the 3, -1, and we get 3 minus 1, which is 2. And since 2 is not 0, I think we're safe. Right? So in other words, because this function is continuous at the point, right, so this is continuous at 3, -1, then we can find the limit just by plugging in 3, -1. So 2 times 3 minus -1 over 3 plus -1. So 6 plus 1 over 3 minus 1, we just get 7 over 2, right? 3.5. So that's the limit, right? That's the limit as we're approaching 3, -1. Okay? Right, again, just knowing that it's continuous. You can plug in the x and the y. Right, obviously this would be a much harder problem. So let's consider this for the moment. Let's find the limits, same function, but now x and y are approaching 0, 0. Okay. So now the issue is the denominator actually is 0. Right? So yeah, so this in number 4 here, this part 4, this breaks down. We can no longer calculate the limit by just plugging in 0 and 0 here. Right. So what can we do? Well, you can do the same thing we did before, use polar coordinates. And I think you kind of get a mess here. Essentially, the r's will cancel out, and this will depend on theta, right? So if we convert to polar coordinates, we're going to get some rather complicated expression, right? 2r cosine theta minus r sine theta all over r cosine theta plus r sine theta. And when you factor out the r's, you get this, right? So as long as r is not 0, you can cancel them. And so you get this, again, rather complicated expression for theta. So all we have to do is find two different angles, right? Say pi over 6 and pi over 3. Oh. And when we plug those in, we should get two different answers. And right, if the limit exists, it has to be the same for any angle. Any theta has to give you the same limit. Right? And we could probably find a theta. We could probably find two different thetas where they are equal. But it has to be true for any theta. So all we have to do are find two different angles where they're not equal. And I think pi over 6 and pi over 3 would work, right? In other words, when you plug them in, I think you'll get two different answers. Or if by coincidence you do get the same answer, just keep it simple. How about 0 and pi over 2? So when you plug in 0 here, theta equals 0, the numerator is 2 and the denominator is 1, so you get 2. When you plug in theta equals pi over 2, you get negative 1 divided by positive 1. You get negative 1. So yeah, if you don't get the same thing, for sure we can say that this limit does not exist. Okay. So there you go. Yeah. So yeah, again, example 4 was supposed to be the easy one. Example 5, a little bit trickier because that's when the denominator is 0. All right, here's another question. All right, so determine all points xy at which the function f of xy is equal to the square root of x plus y is continuous. Right, so you have a function defined as the square root of x plus y. Right, so where is this continuous? Or is it? Right. So of course it's going to be continuous at some points, but not at others. Right? If it helps, go back to your Calc 1 rules, right? You know where this is continuous, right? Essentially everywhere on its domain, right? Its domain is x is greater than or equal to 0. So it's continuous on the interval from 0 to infinity. And technically it's only right continuous at 0, right? Because the limit from the left does not exist. If you try to take the limit as x goes to 0 of the square root of x, technically this limit does not exist, right? Because it's from both the left and the right. However, because it's the endpoint of the domain, we don't make that distinction. We just take the limit from the right, which is indeed 0. So, right, so short answer is it's continuous everywhere on its domain for x greater than or equal to 0. So how does that help answer this question? Well, right, essentially just do the same thing. Take whatever's under the square root, in this case x plus y. Well, that has to be greater than or equal to 0. Right? So there you go, right? So the function f is continuous on the domain, on the set of points x and y, such that x plus y is greater than or equal to 0. Right. So what does that mean? What points are these? Well, if it helps, right, you can solve for y here. Y is greater than or equal to negative x. So y equals negative x is just this line here. A little sloppy, but pretend it's a line. Right? So this is just y equals negative x. So where is y greater than or equal to negative x? Above it, right? Everywhere above that line. So essentially the entire half plane here. Everywhere above y equals negative x. So at all of those points, any point in that region, it'll be continuous. Right? Any point not in that region, so right, let's say we're at negative 2, 1. Right? This will not be continuous. And in fact, you can try plugging in negative 2, 1 and see that you don't get a real number. You get I, imaginary numbers, and we just ignore those. So yeah, anything below the xy plane here is essentially where you get your imaginary numbers. So the function will not be continuous there because, well, we don't even define it when you get imaginary numbers, right? So the set of values for f, the range of the function, has to be real numbers. And in this case, those real numbers will be greater than or equal to 0. as long as x and y is somewhere in this upper half plane here, right? Okay. So we've been talking about limits for functions of 2 variables. Here's a function of 3 variables, x, y, and z, right? So more or less, all these same rules apply, whether they're functions of 2 variables or 3 variables or 4 variables. Everything applies. And so, right, so we have another rational function. And again, the only thing you have to worry about when you have a rational function is the denominator. The denominator is y plus z, but we're approaching where y is 5 and z is negative 3, so we get 2, which is not 0. So there's no issue here, right? This is going to be a continuous function at this point, at the point 2, 5, negative 3. So you just plug in the numbers. Right, plus negative 3, right? So you get 14 over 2, you get 7 as your limit. Right. Of course, that's the same thing you get when you just plug in the numbers, right? If this function is defined to be weird, so x squared plus 2y divided by y plus z. So if you evaluate f at 2, 5, negative 3, of course, you still get 7. That's the, I was going to say z value, but that's the w value, right? This is a function of x, y, and z. So the values, we go backwards and say it's w. Right. But that's not unexpected. That's what we get because we know it's continuous. Remember, the definition of continuous is that if the limit is approaching, say, x0, y0, z0 of the function f as a function of x, y, and z, if you plug in x0, y0, and z0 and you get the limit, then you know, right, f is continuous at that point. Okay, so that's, again, very important point is, right, when is a function continuous and when it's not. And if you know a function is continuous, that generally, although not always, that generally makes it easier to find the limit. Right? If you don't know if the function is continuous, then it's going to be a lot harder to determine the limit, right? Okay, so yeah, all these rules apply here. Let's do one last example. So evaluate the limit as xy approaches the origin, 0, 0. So these are both supposed to be zeros here. Let me try that again. And the function is x minus y over the square root of x minus y. Okay, right. So obviously we can't just plug in 0. If we do that, we get 0 over 0 again, which is not the answer. It's never an answer. So what could we do here? Well, kind of the same thing you did in Calc 1, right? You could try to simplify this expression. And one way to simplify it is maybe to rationalize the denominator, right? If I multiply the denominator by the square root of x plus the square root of y, square root, right? Let's see what happens. Right. So the denominator becomes, well, when you multiply it out, you just get x minus y, right? And the numerator contains a factor of x minus y. So we can cancel, right, the factor of x minus y. And after we do that, it looks pretty good. We just get the square root of x plus the square root of y. Right? And now there's no issue. This looks like it's continuous at 0 and 0. You just get the square root of 0 plus the square root of 0 is 0. So the limit should be 0, right? So I'm letting you think about this for a little bit. Think through this carefully now. We did one similar to this a little bit earlier. So the answer is no. This is not 0. So, yep, here's our mistake, right? We didn't do anything wrong here. You can simplify, right? So it turns out after you simplify it, it turns out you do get the same thing here, square root of x plus the square root of y. But this is not equal to 0, right? In fact, this limit does not exist. So this does not exist. Okay. So let's draw this out. Let's draw out the domain here. Right, we're approaching 0, 0, which is the origin. It's right there. And what am I allowed to plug in for x? Well, because you're taking the square root of x, right, that tells me that x has to be positive, or at least non-negative, right? And the same is true for y. Y has to be non-negative. So we're only allowed to plug in points here, right, in the first quadrant. So as long as you approach the origin in any of the, oops, sorry, I went a little overboard there, in any of these directions, then it looks like you get 0, right? But remember, the whole idea of a limit, you could draw a disk around it. You have to approach that point, the origin, from any direction. So what about this direction? What about this direction? Or this direction? Right? For all these directions, it's outside the domain. So no, right? So you cannot approach the origin 0, 0 from any direction, because this will not be defined if either x or y is negative, right? Or if they're both negative, right? You just don't get anything that way. So for that reason alone, the limit does not exist. Okay, so yeah, this is a tricky one because you might be tempted to just plug in 0 and 0. But as I mentioned some 15 minutes ago, if you try to take the limit as x goes to 0 of the square root of x, right, you don't get 0. This limit also does not exist. So even from calculus 1, this limit does not exist, right? Now, if I said find the limit as x goes to 0 from the right, sure, then you just get 0. Okay? But remember, in 2 dimensions, there is no just right and left. There's up and down, there's all these diagonal lines. So that's what makes these limits here a bit more complicated than from Calc 1 when you only had 2 directions, right? Right and left. You're either approaching from the right or from the left. And if you're approaching from the left, that limit, again, does not exist. And so from, right, when you're approaching 0, that means from both the right and the left. And if you don't get the same answer for both, the left and the right, then the limit does not exist. And so that's what happens with the square root function. So, yeah, it's very similar to this one here. Whenever you're dealing with square roots, you better make sure that, x and y are, are not negative. And if you're approaching 0 from all sides, from all directions, some of those x's and y's could be negative. And that's the issue. Okay, so that was a tricky one. If you're not careful, you might say the limit is 0. Believe me, I think we've all made that mistake in the past. But yeah, so that's something you got to get used to here. So as far as calculating limits, I'm not going to ask you to do it by the epsilon and delta definition. If for most practical purposes, it's just not necessary. If you want to go on to, higher level math courses, say a course in analysis, right, real analysis, then this is all you do, right? You do a whole bunch of proofs using epsilons and deltas. And so if you're interested in math, you might want to look at those epsilons and deltas a little more carefully. And it might not make much sense on the first time you try it. But if you can at least just get the idea of it, or maybe get one example, that will help a lot going forward. If all you want to do is engineering or physics, you probably don't need the epsilon and delta. So we're not gonna do much of that here. I mean, look, they will come up a little bit later when we talk about differentiability, but again, we won't spend a lot of time on it. Maybe just to do one example or so. So yeah, so I think all the homework problems are designed so that you don't need the epsilon and delta definition, probably for a good reason. It's just a little too complicated for a first pass here. Okay, that's all I wanted to say. So that's limits, and then once you have the idea of a limit and continuity, you can take derivatives. So then we'll talk about ways of taking derivatives of functions of, say, 2 or 3 variables. So that's in the next video.